thank you very much, Delphine. Yeah, you mentioned QPMR algorithm. Yes, so this is actually I keep saying that I developed it as a byproduct during my PhD because I needed somehow compute the roots. So I'm happy that people still are using that. Okay, so first of all, let me thank the organizers for organizing the event and for giving me the opportunity to show our results. So the title of my presentation of my plenary is semi-plenary is optimized active vibration absorbers with time-delayed feedback for non-collocated and multidimensional applications. Yeah, so I will briefly first introduce or recall the concept of delayed resonator, yes, so which was developed by Nejat Olgac in the 90s and his co-authors and co-workers. Then my main topic, my two main topics are non-collocated vibration absorption and multi-dimension vibration absorption, yes, which are a bit hopefully advanced, but not that much from the time delay theory point of view. Because is it okay now with these? Because both were switched on. Yeah, because actually we use very simple algorithm, but we put a bit more theory on structural optimization of the system, yeah, the mechanical system which we work at. Yeah, so usually during plenaries people thank to the collaborators at the end, but I have to do it in the beginning because it's really a joint work of many people, of many universities or departments. First of all, of course, Nejat Olgac introduced me to this topic. It's more than 10 years ago when we started this topic together. And then, of course, I need to mention Wim Michaels. Yeah, so we've been collaborating together for more than 20 years. Yeah, time is running. Who brought some numerical analysis and spectral optimization or higher level of these things. Then you will see that I also have root dominancy involved in the talk, like we saw presentation of Rifat Sipahi. So he also involved root dominancy, so even here you will see it. And then from our faculty, I need to mention my colleagues from department of course, root dominancy, Silviu Niculescu and Islam Bousada were included. And for the structural analysis, I need to mention colleagues from our faculty, a department of mechanics, and also colleagues from my department. Actually, quite some people made a PhD on the topic. Dan Pelbauer, Vladimír Kučera is not the famous one. It's my student who coincidentally has the same name. Matěj Chan is working about a bit on a bit a different topic, but it's also related. And Adrian and Adam are finishing their PhDs. Yeah, so let me recall briefly the state of the art on delayed resonator. Yeah, so the story started in the 90s of the last century when Nejat Olgac and his co-authors proposed the actually the fancy feedback for the active absorbers to make the implementation useful and easily tunable. Actually, they stopped working on it around the beginning of this century. Yeah, but in the first decade, or in the second decade of the century, we recalled the topic and started to work on it. And not only us, but also other people, yeah, Ali Ergens, then Jimbing Gao. They did recently very nice results on fractional order delayed resonators, and also Liu and Cheng together. You see, Nejat Olgac is always behind. Yeah, so let me recall how it works. Yeah, so we have a mechanical system, so we call it a platform, which is a second order oscillator, which is being excited by a harmonic force. Yeah? So it's a single harmonic force. And for suppressing its vibrations, yeah, so we can mount a passive absorber. Yeah? So to make it work better, yeah, so we use active feedback U. And it's important to say that the active feedback is taken only from the either position, velocity, or acceleration of the absorber. Yeah, so the platform model is not involved at all. Yeah, and it works like that, that we actually assign a pole, yeah, a single pole at frequency omega to the absorber, and it became automatically a zero of the receptance, which is a transfer function between the excitation force and the position of the platform. Yes, when we have the zero at the j omega, yes, so the signal at this frequency does not pass through the excitation force to the position, and we have ideal suppression. Yeah, so this is actually first setup which we built 10 years ago. When you see, yeah, so this is the platform. It's being excited by this linear motor, and the absorber is here. Yeah, so now it's combined with the position. So let's. Okay, so the idea is, of course, you could see that the platform was silenced after the absorber was switched on. The vibrations were suppressed, but it is, of course, at the cost of large motion of the absorber. Yeah, so because we need to create a sort of an anti-force here to the excitation force. Yeah, so we need a larger motion. Okay, so as I've mentioned, the feedback can be taken either from position, velocity, or acceleration of the absorber. Yeah, so the platform is not involved, so we can then take the tuned absorber and put it anywhere we want to suppress the vibration. Yeah, so this is the advantage. Yeah, so one could ask why a time delay algorithm? Yeah, so could we use, for example, PD algorithm? Of course we could. Yeah, so we just need two parameters to tune and place the root at the imaginary axis. Yeah, but the time delay feedback has some advantages because it's we just need a single measurement. Yes, in the case of PD, we either need to measure both position, velocity, or somehow derive numerically the velocity from the position, for which you need to introduce filter, and you just deteriorate a bit your performance. So we just need a single measurement, and another advantage is that the vibration suppression is very sensitive to small system model mismatches. Yeah? And if you close any loop, you always have a delay there. Yeah? So due to sampling or involvement of the filters in the loop. And actually, if you have a delay in your controller, you can compensate these internal delays and make it really work ideally. Yeah. So another interesting thing is that when we use the acceleration feedback, so we end up with a neutral system. Yeah? So it's also challenging a bit from the theoretical point of view. If we use position, velocity, we have retarded system. Okay, so let me mention the first result on the first contribution, which is just in substitution or substituting the lump delay with a distributed delay. Yes, and this distributed delay can be considered, or is basically the FIR filter, which can be used or partly uses or partly performs the filtration of the acceleration measurements, which are usually noisy. And secondly, so this feedback, or through this feedback, we can remove the neutrality. So we have the cancellation of the term in the of the power of S. So even though practically or theoretically it's still neutral system, its spectrum is degenerate and has retarded features. Okay, so far I talked only about the absorber. So which is our active absorber resonator. But let's also look at the other issues. Of course, one thing is that we want to suppress the vibration at the given frequency, for which we tune the resonator. But altogether, we need to have everything stable, which is not automatic, because we have not involved the platform to the synthesis, and because we place the root at the imaginary axis of the absorber, so it can have some destabilizing effect on the overall dynamics. So we can check. First of all, it's good to have the resonator itself stable, so which is not also automatic, because we place a single root, but we have infinitely other roots, which some of them can be on the right-hand side. So if you have a neutral or acceleration feedback with lump delay, we can have even infinitely many roots. So actually, we can for all the variants of the resonators, we can build some maps, stability maps. So here you see how they look for the acceleration feedback, and here how they look for position feedback. And then, of course, we need to check whether also the stability of the overall system is stable. So for that we can use either QPMR or TDS control toolbox by Vim, or TraceDD, or DDBIF tool, or whatever. Okay, the second thing is that we actually suppress the vibration pointwise. So we put only a single pair on the imaginary axis. So which when we look at the transmissibility on the Bow diagram, it actually causes a pointwise vibration suppression. And if we have some mismatch between the design and true excitation frequency, so we lose quality of vibration suppression. So it would be good to have something like this, to have a broader band, so where we suppress the vibration and to have this insensitivity. Actually, first works or first results on this were obtained by Dan Pilbauer, who was a joint PhD student of me and Wim Michaels. Currently, he's working on a European South Observatory, and he's suppressing vibrations at the mirrors of the telescope in Chile, or for Chile Observatory. Okay, so he used some optimization, or he turned it to optimization problem and solved it by Hanzo. Actually, I would like to say a bit more about the second approach, which is based on placing a double root on the imaginary axis instead of the single root. So this is work which we collaborated together with Islam, Bousada, and Silviu Niculescu, and also Wim Michaels was involved. So actually, look at the setup now. So we consider that we have a controller at the active absorber, but we will see that that placing the double root on the imaginary axis causes destabilization of the whole system. So we need to also stabilize it back. So we consider that we have a second controller here at the platform. And we assume that that excitation frequency omega is not fixed, but can be perturbed. Okay, so this is how the feedback looks like. So we actually turn the system to this dimensionless form. So we have only a single parameter is damping. So which actually helps to generalize the results. So these results are general. So if we have different parameters, different excitation frequency and different absorber natural frequency, so it can always be turned to this form. So for this type of general system, we design this type of distributed feedback. So you see that actually again we take the measurements from acceleration, and it's here is the impulse response. So it's nice FIR filter. We better call it, we like to call it the distributed delay. Okay, so its impulse response is finite, and it brings, of course, some filtration aspects to the design. Okay, and for designing all these parameters, we used the results on root dominancy by Islam and Silviu. And actually, it gives us these parameters. So this is one thing. So we are able to nicely place the double root at the imaginary axis. But you know that if we have a single root at the imaginary axis, the system becomes quasi-stable. But if we have a double root, so it's unstable itself. And it has also a big destabilizing effect on the platform itself. So in our procedure, so first we design the distributed delay feedback to place the double root, and then we stabilize it using a dynamic controller and using TDS control of Wim Michaels and his co-workers. So for that we first turn the whole closed loop system to do delay differential eigenvalue equations, and then use TDS control. So this is these are the results. So we applied or we tested it on improved setup. So now you will see the newer version of the previous one, and here is the implementation. Both the dynamic controller as well as the distributed delay are implemented in a National Instrument compact trio using LabVIEW. We have two voice coil linear motors. One is used for exciting. The exciting, actually, it is used for both, exciting and also partly for stabilization. So that time we didn't have two, so we use one for both. And here is the absorber. So this is a linear voice coil with some added mass, which is sliding on some bearing. Okay, so from transmissibility, you can see that relay we got lower sensitivity. So the red one is for a double root, the blue one is for a single root at the imaginary axis. Also in the spectrum, you can see that relay it is a double root because we have intersection of two curves representing the zero isolines of real and imaginary parts of the characteristic function. And you see that when placing the double root, so we got unstable system. So the blue circles are the spectrum after placing the double root at the imaginary axis, and it was stabilized by PIM software by minimizing the spectral abscissa. So the final spectrum is this are these red crosses. So it's safely stable. And here on comparison of simulations, you see that it's really, we got a better vibration or better or lower sensitivity to vibration suppression. So the red is for the robust resonator, the blue is for the classical resonator. And so this is for 5% mismatch and 3% mismatch between nominal and true excitation frequency. So finally, we have here the experiment. So we excited by this voice coil, inner voice coil, and here, so we have the performance. You may notice that still we have some residual vibrations here. That time, which is the time we use actually relay acceleration sensor for the measurements, which was a bit noisy. So we were not able to tune it. As you will see, currently we switched to position feedback, which is better, a bit better. So here we. No. So now we see that we have the 3% mismatch between the frequencies, and it also worked for that 5% mismatch. So I cannot just. Okay. So these were the results on the robust suppression. Time is running very quickly, so I have to proceed further. Now let me start the second problem I want to show you, which is a non-collocated vibration absorption. So it's a sort of an extension of delayed resonator concept, but now so we have a bit more complicated structure, which consists of many bodies or sub-bodies cards, and the actual goal is to suppress vibrations in a different card from the one where we have the absorber. So the absorber is our delayed resonator is placed here, in this case at M2, and we actually want to suppress the vibration at M6. So for that we need to involve the dynamics of the wall part, so which is between M6 and the base, and tune the absorber for that part. So it's not enough now. It's not sufficient just to look at or involve parameters of the absorber itself. And we actually want to again use a simple structure controller. Actually, this topic was open by Nejat Olgac and his student Jenkins in 2019 and 21. They had 2 papers, but after that actually they found out that something similar was done by Filipovic already in 2001, but this paper was somehow unnoticed, despite the fact that Filipovic actually spent some time with Nejat, and they also have joint papers. Yes, but they use a different control algorithm. So they didn't use delayed resonator, but some dynamic feedback. Okay, so our main contribution to this work is that is the experimental validation, on our setup, and also we actually designed or redesigned the tuning formulas for for the setup with arbitrarily large subbodies. Yeah, so the D can be arbitrarily large for this approach, because Nejat, as well as in the work of Filipovic and Schroeder, these are based on quasi-polynomials, on characteristic functions, yeah? So which has some limitations due to numerical issues. Yeah, okay, so for this arbitrarily large T, we show that actually, yeah, the design remains similar, yeah, to design of the late resonator. We only need to look at the poles of the resonance substructure. Yeah, so we place the pole, the zeros on the imaginary axis, but not for the resonator itself, but for this wall subsystem. Yeah, and they become, or these rules become the poles of the overall system. Yeah, so in our study, we actually divide the system into resonance substructure, where we have the resonator, then we have the target body or target card, which is supposed to be stopped, yeah, silence. Yeah, so here we want to suppress the vibration, and then we have the other part with the harmonic excitation force, and still we want to use a classical position feedback. Yeah, okay, so then here are the formulas. Yeah, so it's not that interesting. Let us study or look how it looks in practice. Yeah, so what we wanted to do, we wanted to show that for a given frequency, yeah, so which is not that arbitrarily, we want to stop one by one the cards. Yeah, so first card we have the absorber, then the second card, and the third card. Yeah, just one by one, using this simple feedback. Yeah, so all the time we just take the feedback from the position of the absorber. Yeah, even though we measure positions of all the cards, yeah, so they are not used for feedback, they are just used for measurements. Yeah, again, it's always implemented on this compact trio. And actually, if you look at the stability picture, yeah, so we want to have the resonant substructure stable, and also the overall system stable. And we want to have them for the frequency in all the cases. Yeah? So if you want to stop the M1, M2, M3, and actually if you look at it, yeah, so these are computed or numerically computed spectral abscissas, yeah, of the system and of the resonating of the resonator substructure. Yeah, so we see that we have really small stability windows. Yeah, so here we have one close to 4 Hertz, another here, and another here. Yeah, actually, theoretically, it would be better, yeah, to validate it or validate the algorithms in the higher frequencies, yeah, where by theory the system should be more stable, or it should be easier to stabilize it, but unfortunately it was not possible due to hardware limitations. Yeah, so because the delay was too small, yeah, for our sampling rate 1 kilohertz. Yeah, so we just chose, yeah, for validation the frequency close to 4 Hertz. Yeah, so these are the transmissibilities, both diagrams, yeah, from the excitation frequency, the position of that mass which you want to stop, and here is the suppression, yeah, or how it looks like for if we target this 4.2 Hertz. Yeah, so we see that all the 3 transmissibilities are zeroed, and here it is for that 8.3 Hertz. Yeah, so this is a frequency from the second stability window. Yeah, also with silence. Yeah, so now we, as I've mentioned, we switch to position feedback. Yeah, so it's taken. Yeah, so this is the absorber. Yeah, so it's taken. Feedback is taken from this sensor. Yeah, so we use a magnetic incremental sensor, which is quite accurate, and you see that the results are much better, even though it's non-collocated vibration suppression. Yeah, so now we actually silence this card. Yeah, so which is showing this graph. Now we will move to this one. Yeah, and the system is being excited by this voice call from the right. Yeah, so now we stop this one. And then the third one. Yeah, you may notice that we also have the other voice call here, but this one is not used for this application. Yeah, so it is just there. All the vibration suppression is done by this, by active control of this resonator. Okay, so it works. Yeah, so the vibrations can be suppressed. We have shown that we have confirmed experimentally that it's possible. Yeah, so at one by one we can suppress vibration. But if you look what happens with the motion of the other cards, yeah, when we stop one of them, yeah, so the amplitude of motion of the other cards is increased. Yeah, so which can be risky, yeah, from a structural point of view, because it can lead to some higher fatigue. Yeah, so this is one problem. Yeah, so we would like to make the system resistant to that, yeah, to have better properties concerning the fatigue accumulation. And the second issue was the stability. Yeah, so the stability window were very, very small, yeah, for a given structural parameters. Okay, so we decided to target these two aspects, and for studying that, we actually looked or considered the separation of the system. Yeah, so we have the original system with the bodies. Yeah, the absorber is mounted on this P-body, and we want to suppress this body MS. After the vibrations, which are excited from here, yeah, so we have the harmonic excitations. Yeah, so if this body is stopped, yeah, so we can actually split the system to two parts. Yeah, so to the part, yes, because it makes a sort of motionless barrier. Yeah, so we can split it to this vibrating part, which is excited by the disturbance force, and to the resonant part, yeah, so which is the left part, which is excited by the force generated by the resonator. Yeah, and then we have the resonator alone. For studying this problem, yeah, so we moved from analysis in terms of differential equations to analysis in the phasor representation of the system. Yeah, so which makes it easier. Okay, so this is the system representation, the phasor form, and and this is for our original system. Yeah, so you see that here we have the XX, the phasor of the body which we want to stop. Yeah, and when actually stopping it, yeah, so we can split the system to simpler subsystems. Yeah, so this is for the resonating, and this is for the vibrating subsystems. And also we can, after some manipulation, we can express the force for the absorber force, or the force which is being generated by the absorber in terms of the excitation forms, and then we can use it in the synthesis. Yeah, actually, what we want to analyze is the fatigue loading. So how the amplitudes change and how they can contribute to the fatigue. And for quantizing it, we use the elastic potential energy, for each of the link, so which is given by this expression. So we just take the difference between the it's just potential energy, and here we have the stiffness of the springs, and by this we can express this elastic energy for each of the link in the setup. Okay, so then we of course need to design the delayed resonator, which we already know how to do it, but here it's just recast to the expression in terms of that phasor representation. Next to that, we also look at the stability. So we want to have everything stable. So again, we use WIM's TDS control toolbox, and we turn the system to the DAE representation and compute the spectral abscissa. Then the last thing which we could think of is the power needed for vibration suppression by the resonator. So of course we want to minimize the power consumption as well. Okay, so we have plenty of requirements on how it should work. But remember that in the control we only have the two parameters, the gain and the delay. So we need more parameters to optimize everything. So we actually consider as the parameters, as tunable parameters, also selected parameters of the mechanical system. And then we form the objective function. So we balance the fatigue in terms of maximum of the potential energies with the power consumption. And of course we have some constraints on parameter ranges. Then we have constraint on stability, fatigue and the absorber, and of course we want the ideal vibration suppression. If you look at the optimization problem, it's not very nice. Non-linear, non-smooth. Okay, so we could use Hanzo tool, or better in this case we use Granzo. So which is advanced Hanzo with considering the constraints. So we can also use the constraints. And for computational aspects we use TDS control. First, we tested this optimization-based approach on our system. So what we did was the investigation whether we could possibly improve the performance by just slight changes of some of the parameters, and because it's a low parameter system, so we could actually brute force obtain the objective functions. Actually, it showed up that the only parameter which should be tuned is the mass M3. The others are not relevant, and the mass of the absorber. So here you see how the potential energies looks like for when we change the mass of the third card. So here this is the stability, margin, power consumption, and the potential energy of the absorber. Okay, so again we have the video. Where first we show how it looks for the nominal case. So this is so we want to stop this card in the middle, and here we have the potential energies. Yeah, so the lower, the better. They actually changed when we come from the passive here to active suppression. Okay, so now we will slightly change the masses. Yeah, the mass of the card 3. Here you see that here we don't have this extra weight anymore, and we have a slightly larger mass of the absorber. Yeah, so we change the mass by putting or removing the plates, the steel plates. And in the comparison, yeah, so the gray one are the energies for the original system, and the green one for the optimized. Yeah, so now it's much better. Yeah, so by slight changes we can get much better behavior and stable behavior. Okay, so then we also validated this approach on a numerical case study with larger number of cards. Yeah, so we used five bodies, and this time we adjusted the parameters which are listed here in theta. So next to mass of the absorber, parameters of the absorber, we also look at the stiffnesses of the particular springs. What is interesting is that actually in the beginning we considered that for the nominal system we considered that all the stiffnesses are more or less the same. But then by running the optimization method or solving the optimization problem, we were able to reduce the objective function almost 10 times, while, as you can see, the adjustments of the stiffnesses are relatively slight. Yeah? So by small modifications we can get much better results. Yeah, so the optimization problem is difficult to solve. Yeah, so for 100 starting points, yeah, it took about 535 minutes. Okay. Yeah, but it's the way to improve the structures towards vibration suppression. Yeah, so we can involve everything in a single optimization, yeah, like control and structural properties. Yeah, so this is here. Yeah, so how the potential energies were reduced. Okay, so then next to these issues, yeah, so far we assume that we are able to split the system to resonant and vibrating substructures, but this is not always possible. So here we have, for example, a system which is not anymore serial interconnection, because it has here a spring, which is actually connecting the card 0 with card 2. Okay, this work has been solved mainly in collaboration with Wim Michels, by postdoc Heiksilm and by Adrian Seldenha, who is about to complete PhD thesis soon, hopefully. And I will not show more on it because you will see it in Wim's talk tomorrow. Yeah, so you will see also the validation on the experimental setup. Yeah, so it works. Yeah, so the first work by Haik used time delay feedback, not only for the resonator but also for stabilizing controller, and Adrian used classical output feedback, yeah, for an output which is slightly delayed. Yeah, so we assume that we have a small delay in the feedback loop. Okay, so this was the end of the second topic I want to present. I have some time, hopefully. Yeah, so Delphine, I have 20 minutes. Yeah, because we started and yeah, okay, thanks. I will go quickly through that. Yeah, so the second or third thing I want to present is the extension of the concept to multi-dimensional vibration suppression. Yeah, first to two-dimensional and second to dimension vibration suppression. Yeah, so what we want to do is to move the concept here from a single degree of freedom, yeah, so to planar vibration absorption here, which is of course more difficult because for a single degree of freedom absorber you only need a single actuator. Yeah, so if we want to go from 1D to 2D, we need 3 actuators, and if you want to go to 3D, we need 6 actuators. Yeah, so we just move from the SSSC problem to MIMO problem. First, we consider this configuration of the absorber. Yeah, so we have the absorber body and 3 connecting links. I will go quicker through that because it's more like mechanical engineering now. Yeah, so it's not about time delay that much. Yeah, so what we want to do first, yeah, actually we make it reverse. Yeah, so we design the ideal absorber. Yeah, so how it should look like, and then we use time delay feedback for tuning the absorber with current parameters, yeah, to those ideals. Yeah, so mainly we will adjust by the time delay feedback the properties of the links. Yeah, but it's not about the links. Yeah, so we have found out that we also need to look at the mass of the absorber and moment of inertia. Yeah, so they cannot be selected arbitrarily, because what we need at the end is to have 3 eigenfrequencies of the absorber being unified. Yeah, so this is what we want to achieve, and actually we want to merge them or place them to the excitation frequency. Yeah, only in this case we can fully absorb the planar vibrations. And we came to the conditions which needs to be satisfied concerning the mass, moment of inertia, and also the dimensions of the absorber. Okay, and we show that yeah, of course we are working with MIMO systems, yeah, so we need to look at the singular values, and actually if they are boosted to infinity, yeah, through turning the physical absorber to the ideal absorber, yeah, so we really can get the ideal vibration suppression, which is shown on this slide. Okay, so then once assume that we already have the absorber which can potentially be, or which can be unifrequency. Yeah, so what we need to do is to just turn the current absorber, which is not ideal. Yeah, so it has stiffnesses which doesn't have to be ideal, and it has some damping. Yeah, so we need to turn it to that ideal vibration absorber. Yeah, so this one comes from the mechanical design, but in reality we have this one. Yeah, so what we need to do in each of the links. Yeah, so we only need to remove the damping, remove the effect of damping, and change the stiffness from the current to the ideal. We cannot do it for frequencies, but it can be relatively easily done for the single excitation frequency. Yeah, so here we see the difference between the true stiffness to ideal stiffness, and this is the damping which we want to remove. Okay, in theory it works. Yeah, so we place the frequencies on the imaginary axis, all is stable. Yeah, so the Bode diagram works fine, and also vibration suppression as well. Yeah, so theoretically it can be done. Yeah, so then the following question was whether we can do something also with the links. Yeah, so with the parameters of the physical absorber, yeah, of the links of the physical absorber, whether then can be left arbitrarily selected, or whether it is better to put some specific values. Of course, it's better to put some specific values. So we show that if we select properly the ratio between the absorber link properties, stiffnesses and damping. So we can actually physically decouple the system, and then we can use results which were derived for a single degree of freedom vibration absorber to a multi-degree of freedom vibration absorber. So this is a characteristic function. You really see that it's decoupled, and we call this absorber zeta omega to the unified to the absorber. So this was first derived for this Stewart platform-like configuration. So I will skip this one, and so as I mentioned, by actually decoupling physically the absorber, we can use the result which are derived before for 1 degree of freedom absorber, including the stability posture. Because it would be much more difficult to do it for the general absorber. Because we would have 3 different gains, 3 different delays, and then the stability map would be much more complex. Okay, so on that problem, Wim Michels was working with us, and then he came with the idea. So why do you consider this asymmetric configuration, which is actually sort of natural from mechanical engineering point of view? So why don't you use something which is symmetric? And of course, it's much better to do that, which we showed in the subsequent analysis. So now we assume that we have the absorber of this shape and 3 connecting links, and we have a sort of a symmetry. And we can again take it to this unifrequency form and damping form, unifrequency and unidamping form. And what we did next, we look also on the energies which is needed for the vibration suppression. And we did a comparison of the 2 absorber types. So you see that we have here the animation, the symmetric, asymmetric absorber. It's fixed to the platform, which is now moving. So now it's in passive regime, and you can see here the excitation force. And on this graph, we have the power distribution in the particle links, so which agree with the color. What is interesting that actually for both absorbers we have exactly the same behavior. So which is due to turning them to that unifrequency form. But what difference is the distribution between the power in the links? So maybe the best is seen that the symmetric is better for exciting the platform in its center, in the angle which corresponds to the angle of this link, in the asymmetric one. So we see that actually here for this asymmetric case, this link is active while the others are not. So which can result in some fatigue within this link. Compared to that, in the symmetric one, we have actually a bit better distribution. Always at least 2 links are active. So we also consider the case of rotating force. And currently we are also working on experimental validation, which is much more complex compared to this to 1D problem. You see here we have the absorber. We have 3 active legs, active links. So again we use these voice coil linear motors. and it's being put on a platform which is actually excited by the excenter, which is on the other side. Yeah, so here are the first results, just taken on mobile phone. Yeah, so the quality is not very good. Yes, so you see that it's now excited by this excenter. Yeah, so now the absorber is not working. Actually, it showed up that that even though we used quite fine, quite fine bearings, yes, still it shows that the friction plays a big role. Yes, so we have to also include the algorithms for compensating the friction, yeah, in the links, and then on top of that we use that delayed resonator or delayed feedback for each of the link. Yes, so now you see that after putting these two things, the platform was silenced. Okay, so I have a couple of slides on moving it to three-dimensional vibration suppression. We actually have two variants. Yeah, so the first one is on extending this asymmetric configuration, and then also the symmetric, which again was proposed by Wim. Yeah, that why not we use something which looks like a cube, yeah, with the springs and with everything symmetric. And the extension is not that straightforward. It was mainly shown on that Stewart-like platform, because from the structure analysis it showed up that we are not able to unify all 6 eigenfrequencies, yeah, for this case. Yeah, so it's not possible to only turn it to ideal absorber by modifying the link properties. We also need to have an additional controller. Yeah, so maybe it's shown here. Yeah, so after using only the time delay feedback, we can place 5 eigenvalues, yeah, to the excitation frequency, but one is aside, and that needs to be that this pole need to be placed here by additional torsional feedback. Yeah, so at the end we have the ideal behavior. Okay, so it works on simulation. And in that cubic configuration, it is much more convenient. Yeah, so it can be done perfectly. Yeah, so the results are straightforward. Yeah, so this is the next challenge to validate the results for 3D vibration suppression experimentally, which will be a real challenge. Okay, so by simulations we not only tested it on some artificial or academic problem. We actually tested on some numerical case study. We got data from a company, from some application with large rotating machines. Yeah, I cannot specify. They don't want us to spread the information, but it was also validated for some practical problem, numerically at the moment. Okay, so let me move to the acknowledgements. Yeah, so first I would like to thank to all the collaborators, and also to our founders, which is at the Czech site, mainly the Czech Science Foundation. Here we got a couple of projects on the topic, multidimensional, also for non-collocated. Currently we are solving or moving a bit more to the nonlinear systems. We have a joint project with Sergei Chelikovsky from Academy of Sciences on considering also the nonlinear aspects. Yeah, and then this is the acknowledgement to RoboProx, our current big project. Okay, thank you very much for attention.